Hello everybody, get ready to do lesson 4.5, part 3 of pre-calculus math today. Graphs of sine and cosine functions. Part 3, you have 2 points here, it goes in your notebook. Today you got 34 points on your classwork sheets. And we'll start right in here for a notebook entry. The final type of transformation is the vertical translation caused by the constant d in the equation. So y equals d plus a sine quantity bx minus c, and y equals d plus a cosine quantity bx minus c. The shift is d units upward for d greater than 0, and then d units downward for d less than 0. Students, this goes in your notebook. In other words, the graph oscillates about the horizontal line y equals d instead of about the x-axis. Let's try one of these now. Vertical translations. Use a graphing calculator to analyze the graph y equals 2 plus 3 cosine 2x. So the amplitude here is 3. Here's our amplitude. And the period is pi. See, our pi is 2 pi over 2, so it will be pi. The key points over the interval 0 pi r 0.5, pi over 4, 2, pi over 2, negative 1, 3/4 pi over 2, and then pi over 5. So we're starting from 0 and then going to pi because that is our interval. So graphing those here's your plots for an interval. This is an interval here. So then this would be your graph here, your continuation of that one interval. Here's the interval we plotted, y equals 2 plus 3 cosine 2x. So compare with the graph of f of x equals 3 cosine 2x. The graph of y equals 2 plus 3 cosine 2x is shifted upward 2 units. So for that, okay, so for this problem here, use a graphing calculator to graph this function here, y equals negative 4 plus 5 cosine pi t over 12, and then include 2 full periods. Identify the amplitude and the period of the graph. So amplitude here is 5, and then our period here would be 2 pi over 12. This is our b here. And then for this here, for negative 4 would be our shift in our graph. So instead of having an amplitude of 5 above and below our x-axis, we have a shift down here downwards of negative 4. So up here, our max and our min, our max would be positive 1, and then our min would be negative 4 and 5. Amplitude there would be negative 4 down here, would be our min on that one. Okay, let's try another one. Example 7, finding an equation of graph. Find the amplitude, period, and phase shift of this sine function here, whose graph is shown. Write an equation of this graph. So the amplitude of this sine curve is 2. Here is an indicator here that we have an amplitude here of 2 up here, then 2 up here. So we have a max of 2 and then a min of negative 2. The period would be 2 pi. So from here, from here to here would be 2 pi. This would be negative pi over 2. And there is a right phase shift. So for this, it's been shifted to the right. This usually would be over here. So we know that much. So right phase shift to pi over 2. So you can write y equals 2 sine x minus pi over 2 would be our phase shift. This negative pi over 2 means that you do shift to the right pi over 2. So let's try one now up here. So we have these graphs here, and we're going to find a, b, and c for the function f of x equals a sine quantity bx minus c, such that the graph of f matches the graph shown. So we have a situation here where amplitude is 3, so we have an amplitude up here of 3. So it's positive 3, negative 3. Since the graph is reflected about the x-axis, we have a equals negative 3. So our period here would be 2 pi over b, which equals pi. Therefore, b would equal 2. So our b would equal 2. Our absolute value will be 3 here on our amplitude. And then our phase shift, c equals 0. Thus, f of x equals negative 3 sine 2x. So we have a phase shift here of 0 because this would be a sine function that goes through the origin. And so this is what our function would be for this graph here. And then down here, amplitude is 2. We know that a equals 2. Period would equal 4 pi. From here to here would equal 4 pi. And then 2 pi over b would equal 4 pi. So we know this has to equal 2 pi over b. Therefore, b would have to equal 1/2. So we can plug that back in. Our phase shift would be c equals 0. Again, this is another sine function. So here is our a is 2, our b is 1/2. This is our b. And so it would be 2 sine of x over 2 would be the function for this graph here. Let's try another one here. Example 8, find a trigonometric model. Throughout the day, the depth of water at the end of the dock varies with the tide. So here's our tide chart here for that. Use a trigonometric function to model the data. Let t be the time t equals 0 corresponding to midnight. So t equals 0 would equal midnight. Do we see midnight? Here's midnight here. So 3.4. So begin by graphing the data. So here is a graph here of the depth of water with time. And we sort of get kind of a trigonometric graph there going on. So you can use either sine or cosine model. Suppose you use cosine. So we're going to try cosine here. Y would equal a cosine quantity bt minus c plus d. So the difference between the max and min height of the graph is twice the amplitude of the function. So we have an amplitude up here. So it'll be 1/2 maximum minus a minimum. So we have 11.3 up here minus 0.1 down here, which would equal 5.6. So 5.6. Cosine function place 1/2 of a cycle between the times at which the maximum and depths occur. So the period p equals 2 times time of min minus time of max. So the time, now we figure in time here, which would be our p here, our period, which would equal 12. So which implies that b equals 2 pi over p would equal 0.524. Also, high tide occurs 4 hours after midnight. Consider the left endpoint to be c over b equals 4, so c would equal 2.094. Moreover, because the average depth is 5.7, it follows that d equals 5.7. So you can model the depth with the function y equals 5.6 cosine quantity 0.524 t minus 2.094 plus 5.7. So that would be one possibility for that. B, a boat needs at least 10 feet of water to moor its dock. During what times in the evening can it safely dock? So for that, using a graphing calculator to graph the model, we come up with this model here. So during what times in the evening? So it has to be in the evening. And so that wouldn't be in the evening, but this would, 14.7, 17.3. So 14.7 would be 2.42 p.m. or 2:42, and then 5:18 p.m. for 17.3. So that would be one way that you could derive your times of the day that you would have 10 feet of water with that tide chart. And using the intersect feature down here of y equals 10, you come up with your intersections here for that function. So let's create a scatter plot here for this situation here. Here's a table here. The percent of the moon's face that is illuminated on day X of the year 2012, where X equals 1 represents January 1, is shown in the table. So here is our table here for days of the moon's face that is illuminated on day X of the year, the percentage of the moon that's illuminated. Create a scatter plot. Let's create a scatter plot first of that data. This is your scatter plot, and then if you connect it, sure enough, you have a trigonometric model showing for that. And then when you plug this in to do a trig regression, you come up with this model here for this data set. The model, it fits the data well, I suppose, so this will be the equation, rather the function for this data set. Using a trigonometric regression on your calculator, you get a sine function here, and that's 4.5 part 3 classwork. Email me here for questions or course materials. Thank you very much.